verifying activity diagrams in software engineering. In this presentation, we'll be exploring how activity diagrams can be systematically verified and the importance of this verification process in software development. So what exactly are activity diagrams? Simply put, they're visual representations of workflow processes that help us understand how systems operate. These diagrams are important because they clarify complex behaviors and interactions within software systems or organizations. When designed clearly, they prevent misunderstandings and significantly reduce the risks of implementation errors. In this presentation, we're focusing on a research paper that extends the toolkit for conceptual modeling, or TCM, with automated verification capabilities for activity diagrams. Let's talk about why verifying activity diagrams is so crucial. First, errors can be extremely costly if discovered after implementation. Early verification saves both time and resources by identifying issues before they become embedded in the system. The verification process confirms that workflows operate logically before any implementation begins. However, this verification faces several challenges. Modern workflows are increasingly complex and difficult to verify manually. Visual inspection alone simply isn't enough to catch all potential issues. Additionally, until recently, automated verification tools specifically designed for UML activity diagrams were limited or incomplete. This gap is precisely what this research paper addresses. The paper presents an elegant solution to these verification challenges. The researchers extended TCM, which was already an automated diagram editing tool, by implementing additional verification capabilities. Their solution automates the entire verification process. It converts UML activity diagrams into a model checker-friendly format, checks if workflows meet functional requirements such as ensuring orders are approved before shipping, highlights errors directly on the diagram if a requirement is violated, and uses formal execution semantics to ensure correctness. This implementation creates a seamless bridge between intuitive visual modeling and rigorous formal verification. The automation of this process means workflow designers can detect logical errors before implementation without needing expertise in formal methods or model checking techniques. We selected this paper because it provides a practical and automated approach to verifying activity diagrams. Unlike previous approaches, it allows direct visualization of potential errors within the activity diagrams themselves. Most importantly, it addresses previous gaps in activity diagram verification, offering a solution that's both theoretically sound and practically useful for software engineering teams. In studying this paper, we hope to learn several key things. First, how activity diagrams can be systematically verified using formal methods rather than relying on manual inspection. Second, how the paper bridges workflow modeling with formal verification, essentially connecting two different worlds in software engineering. And finally, we wanted to explore practical approaches to workflow verification that could be applied in real-world software development contexts.
So how can this be used in practice? One example is it helps ensure business processes like ERP or e-commerce workflows eventually complete. And another example is by integrating these checks into the development pipeline, which lets teams spot errors right after code revisions. This method addresses complex workflows with loops, parallel tasks, and real-time triggers by abstracting the data so we only consider the essential true-false conditions, keeping the model finite and checkable. Finally, compared to Petri nets, it's more intuitive for data and event-driven systems, and unlike older methods, it includes fairness constraints to avoid infinite loops.
Do we agree with the author's viewpoint? Yes, we agree that the model checking is essential for verifying complex workflows, as manual inspection is impractical in this case. The need for strong fairness constraint is well justified to avoid infinite loops in verification, while UML activity graphs offer benefits over Petri nets in handling event-driven behavior. In addition, Petri nets are still widely used and might be better suited for certain cases. Are the conclusions logical? The conclusions are well supported by formal verification methods and experimental results, and their enhancement of the NUSMV for strong fairness checking is a valuable contribution. However, their validation is limited to a prototype, lacking real-world testing to confirm scalability and efficiency in large workflows. There are limitations of the study. First being scalability remains a challenge due to state space explosion in complex workflows. Additionally, the requirement specification method relies on temporal logic, which is difficult for non-experts. Lastly, their verification focuses on the design level, meaning real-world implementation issues could still arise.